In this next video, we talk about the theorem in calculus. It's very important, but he doesn't get a name. And it's essential that this idea is the key, at least for differential calculus. This result, having this result, is the key that unlocks differential calculus. Now, it's pretty straightforward and not super complicated. That's why it really doesn't get a name, but it is a very important idea. And the idea is this: if we have two functions here, f and g, they're identical, exactly the same, except at one single little point c in some interval about c. Okay, so for some interval about c, f and g are identical for all x not equal to c in the interval. And so they're exactly the same everywhere. Then we say if the limit as x approaches c of g of x is L, then since f and g agree everywhere but the one place where the limit doesn't care about what's happening, then the limit as x approaches c of f of x would be equal to L. So let's see what this theorem is really saying by looking at an example. So consider the limit here as x approaches 3 of x squared plus x minus 12 over x minus 3. Okay, that thing does not have a limit, at least in terms of our limit rules we've developed, where we can just evaluate it. Because if we try to evaluate it, we say 0 over 0, and then we're kind of faced with, well, now what? Because our division rule for limits said we could just evaluate the top and bottom as long as the bottom's not 0. Or with our rational functions, right? Every rational function, we can just evaluate them as long as the bottom isn't 0. But now the bottom is 0. And so how do we handle this scenario? How do we handle this situation? Well, that's where this theorem steps in. First, we got to figure out, well, what are my two functions f and g? Well, the original function's f. That's the one that happens to be undefined at, in this case, x equals 3. So we need to find another function g that's identical to f, except they disagree at x equals 3. Right? They're different there. So here's how we find it. Let's take our fraction there. Let's get away from the limit for a moment. Take that fraction and think back to algebra. One of the things you were asked to do in algebra was to simplify. So the way you did that is you factored the numerator, and if possible, factor the denominator. And then we'd look for any common factors that we can cancel out. And so here we'd say, yep, you got a common factor there, x minus 3 in top and bottom. Let's pull it out. And then you write down x plus 4. Okay. And you are wrong. Okay. I taught this, and this is what I teach when I teach simplifying rational expressions, but what we've just written down is actually wrong. Not much, not by much, but it's actually wrong. We kind of leave this step out in like an Algebra 2 class. I really emphasize it in pre-calculus to kind of make sure people really get the idea that, you know, we kind of leave a little bit of information out in Algebra 2 so that we can just make things simpler. But that's actually not quite correct. You see, this thing over here is not defined when x is equal to 3, but this thing over here is. So we cancel it out, x minus 3 over x minus 3, and that's okay. We can do that as long as x minus 3 is not 0, because we can't cross out 0 over 0. So there has to be a caveat, a little carve out, an extra condition here. That simplification is okay as long as x is not equal to 3. As long as x is not equal to 3. If x is equal to 3, then we can't cancel out 0 over 0. And so that's our f function. F is equivalent to the function x plus 4, provided x is not equal to 3. Well then, if that's our f function, our g function's easy. G is just g is just x plus 4 without any restrictions. So you see, g and f agree everywhere except 3. G has an answer at 3, f doesn't. So now we just take the limit of g, and we get 7. Well, since f and g agree, the limit of f is also 7. So that's how that theorem comes into play. Now in practice, we usually don't approach it that way. We kind of boil things down a little bit and make it a little bit less writing. And so in practice, what we do is we would have our original limit problem there, and just like we did our factoring step up above, we'll do that inside of the limit. So we'll go ahead and do our factoring, and then we'll say to ourselves, okay, now we can cancel that out. And in terms of the limit, the reason we can cancel that out is that the limit doesn't care what happens at 3. At x minus 3, when that's 0 over 0, limit's not worried about that. Limit doesn't care about x equals 3. And so we don't worry about x equals 3. So the fact that the limit doesn't care about x being 3, specifically has no interest in that, that's why we're allowed to cancel it out, because it doesn't change the limit. And so then we get limit of x plus 4 equals 7. And that's what we do in practice, but this is all going back, though, the idea of doing that is going back to this theorem. Which is actually kind of a really cool little theorem. It's not overly complicated. It is important, though, because it turns out to do what we're going to be doing later called derivatives, we need to do these 0 over 0 limits.